Doubling a list over and over sounds like it should run forever. It doesn't. And two lines that look almost the same, L.clear and L set to an empty list, behave completely differently. Behind both puzzles sits a single idea. A name is not the object it points to. Start with L holding 1, 2, 3, 4. We write a loop that walks every element of L, and the loop variable is E. Inside the loop, one line. L is set to L plus L. That plus sign is the concatenation operator. It joins L with a copy of itself. Let me give you the answer first, then prove it with a memory diagram. Each time through, this line takes whatever L currently is and doubles it, gluing a second copy onto the end. Watch it double. L begins as one row. 1, 2, 3, 4, first pass. L plus L stacks a second copy, giving 2 rows. Second pass doubles that into 4 rows. Third pass, 8 rows. Fourth pass, 16 rows. Then it stops. Here is the crucial part. The loop runs exactly 4 times, not forever. Why 4? Because E walks the original list, which had 4 elements. Reassigning L never changes how many steps E takes. 4 elements in the original mean 4 passes, and we finish with 16 rows, 64 numbers in all. Let's see why in memory. Originally, L points to the object 1, 2, 3, 4, and E points at its first element, the 1. Now we run L is set to L plus L. Read the right side first. Concatenation never mutates. It builds a brand new object. So a fresh list appears in memory. 1, 2, 3, 4, 1, 2, 3, 4. Nothing has been written back into the old list yet. We have simply created a new separate object sitting alongside the original. Now the left side, what does L is set to actually do? Exactly what it did when we reassigned a tuple. The assignment peels the name L off the original object and pins it onto the new object we just built. Same name, L, now pointing somewhere new. The old object, the very one E is walking through, has lost its L label. Nothing points to it by the name L anymore. The only thread still connecting us to that original object is E, because E is standing inside it, on one of its elements. A student asked the sharp question, why doesn't E move when L is reassigned? The answer is the heart of the whole lesson. E is bound to an object in memory, not to the name L. When the loop began, E was told to point at an element of the object that existed right then. Reassigning L changes what the name L means. It does nothing to E. This is why we insist on separating the object in memory from the name we hang on it. Names get reassigned freely. The object stays put, and E keeps pointing into it. Another student pointed out that a loop usually stops before the last element. That's true when you loop with range, which counts up to but not including the length. But here we are not using range. We are iterating directly over the elements of the sequence. And that visits every single one of them, including the last. 4 elements means 4 passes, first to last. Here's a preview of something we'll lean on. Often you want to empty a list completely, but by mutating it, keeping the same object and just stripping out its contents. The command has a friendly name, clear. Writing L.clear removes every element inside L, leaving the same list object, now empty. It does not build a new empty list. It reaches into the one you already have and wipes it out. How can we prove an object is the same object, and not a new one wearing the same name? Python gives us a tool, the function ID. Calling ID on an object returns its identity, essentially its address in memory, a number that uniquely tags that one object. If 2 moments show the same ID, it is literally the same object. If the ID changed, you are looking at a different object. Let's put it to work. Start with L equal to 4, 5, 6, ask for its ID. It comes back as some long number. The exact value depends on your machine, so treat it as a label. We will watch the last 3 digits and say they end in 808. Now append an 8 to the list. L becomes 4, 5, 6, 8. Check its ID again. still ending in 808. Appending mutated the list in place, so it is the same object at the same address. We changed its contents without creating anything new. Same list, keep going, now call l.clear. The list empties out completely, nothing left inside. Ask for its ID one more time, still ending in 808, exactly as before. Clearing did not hand us a fresh empty list. It mutated the object we already had. Append and clear are both mutations, so through all of it, filling and emptying, the ID never budges. One object, changing over time. Now the common mistake. Fresh start, L is 456 again, and this time its ID ends in 312. Append an 8 to confirm the address holds, still 312. The same object mutated. But now, instead of clearing, we write L is set to an empty list using the square brackets, get the ID again, and it is different, no longer 312. That single line did something completely different. It did not empty our list. It built a brand new empty list and rebound the name L to that. Our original object, 456 plus the 8 we appended, is still sitting in memory. We have just lost the name that reached it. This is the same story as the tuple and as our doubling loop. Assignment binds a name to an object. When we say L is set to an empty list, Python created a new empty object and appointed the name L added. The old list did not change and did not disappear. It simply lost its L binding, orphaned in memory. That is why the ID changed. We are now looking at a different object entirely. Clear mutates and keeps the ID. Assignment replaces and changes the ID. The ID is how you tell the two apart. Step back to the big picture. Lists and tuples both bundle many objects into one compound value. Tuples are immutable, they never change, which makes them perfect for fixed groupings. A country paired with its latitude and longitude, or a word stored with the page and the line where it appears. Lists are mutable, so you reach for them when the data keeps shifting. A roster of employees, a class of students, a grocery list, the food in your fridge, all of these change constantly. A list lets you update the contents in place without copying the entire collection every time, which would be painfully wasteful. So carry three things forward. Reassignment, L plus L, or an empty list, builds a new object and moves the name, leaving the old object behind. Mutation, append, or clear changes the object in place, and when you cannot tell which happened, ask for the ID. The same number means the same object, and a different number means a brand new one. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.